Let's see. Let me make sure everything's working. Take the title and then no projection view. Right. Sorry about the delay, guys. My PC just crashed right as I was about to start streaming. Yeah, I'm back now. Hopefully, nothing happens. I might have to soon upgrade my laptop, but we'll see how it goes. Okay, let me make sure it's streaming everywhere correctly. Okay, Twitch was working. And YouTube is working. Let me just update the stream a bit. Say stream info. Blender and animation kind of. Say Vulkan. C++. Programming. Yeah, done. Now the tag should be a bit more accurate. Yeah. As you can see, I now have some more plugins added. So now I can get errors inline, which is very handy. Then I also got rainbow brackets and also these rainbow indentations, these guides as well. These are all just like nice to haves kind of. Yeah, I won't be applying these warnings yet. I'll wait for like the full tutorial to get over, and then I'll go through and like fix these up if they are required. So let's get into it.
Orthographic projection and perspective projection matrices.
Today we'll be implementing the projection view. Yesterday we were able to add some 3D model, 3D cube, and that was also an orthographic view. So today we'll be doing perspective view.
Projection matrices change the shape and location of Vulkan's canonical view volume. If you would like to know the theory, matrices, you need to get us by adding a new file, lve camera.hp.
Oh, I'm making a camera. Okay. New C++ header file. Only camera. Okay. Save this.
file by adding a header guard with pragma once and my namespace LVE.
I should pragma once. Namespace LVE. Public private we're creating two functions to set the perspectives. Set to graphic view projection. Oh, this supposed to be a class. Class LV camera. This goes inside that. Us. The plugin is already showing its usefulness. Yeah, let's do float left, float right, float top, float bottom, float new, float far. Now word set perspective projection. Why is the Windsurf thing not good? Let's see. Autocomplete, show inlay. Yeah, maybe something I changed here. Inlay hints. Inlay. Let's use editor font for inlay. General. C++, enable inlay hints. Console settings. See, it's under the like autocomplete. Autocomplete. Why is it not working? Okay, let's add this here. Oh,
And
let's
then
do
float
FOV, not different values
bar for
altogether.
the near and far clipping planes respectively. Now we need the camera class to store the 4x4
Yeah, let's do this FOV var float aspect float near, float far. I think it's supposed to be just VFOV.
In a GLM map4 variable. So I'm going to open my model header class just to copy these 3 lines, including the GLM library, and then I'll paste them in here. Then
Let's copy this. Let's close all the other things. There we go.
variable with type GLM map4 called projection matrix and initialize it to the identity.
Have it GLM map4 projection matrix. I'm guessing it will all equal
For
to
the camera header is
1.0.
function for the projection matrix. So add a public function with type const GLM map4 reference called getProjection and mark it const. Then just return the projection matrix.
Okay. Void GL map4 get projection const return projection matrix. Non-const value reference to multiple type identifiers. Okay. That plugin is so handy. It'll save us so much time.
Now let's do the implementation. I will create a new file, lvecamera.cpp.
So let's make a CPP file, new source file, lvecamera.cpp.
And at the top include the associated header with
Include lvecamera.php.
and then I've provided a paste.
Let's add the libraries. std include c so I also realized for anyone watching the stream, this is probably too small. Let me increase the font size. Zoom appearance. Okay, 200% is a bit too much. Can go back to 100 and just increase the font size. That should work. General appearance. Are you going to presentation? So misspelled hash include. Hash include limits. For notification will not yes. Carol settings. Say font size. There we go. Change font size. Live. Okay. Yeah, yes. That should be better for everybody else's
For the functions in
readability.
the description below.
Namespace. We
All these functions literally do is set the projection matrix member variable of the camera class to be the orthographic or perspective matrix. These matrices
let's get the base one. Control A, Control C. Okay, so it was supposed to be make it a capital on Shift F6. Okay, FOV bar, Shift F6. Yeah. It's this here, this here. Okay, now it's correct. Yeah, we're just setting the individual camera position as well. 2.0, 2.0. And dot 0. 0, 0, 0, 0. Don't put Okay, let's leave it at that for now. Actions. Convert to trailing return type. Actions document show project fixes. Okay. Let's continue with the video.
These are the exact results derived in the previous video. The next thing to do is make it so that the render system uses the camera when rendering its objects. So navigate to the simple render system header and include the camera class. And then
A simple render system HPPP. Included. Maybe camera.hppp.
we need to do is update the render game objects function with a third parameter of type const LVE camera reference called
Render game objects const LV camera and the sound camera.
we don't make the camera a member variable because we want to share camera objects between multiple render systems. I'm just going to copy the new function declaration and then open the simple render system.
Yeah.
File. Replace the
Camera. Yeah. Void generate definition. Now let's go to the CPP and copy this. Control C. What is the function? Render game objects. There we go.
function signature with the new one. And then within the function, at the line, we set the push.transform field, multiply camera.getProjection by the object's transformation matrix.
That was a limit push transform. Yeah, okay. Camera dot get projection multiply. Yeah.
Also, this is just a temporary solution. Most game engines will not perform the matrix multiplication on the CPU, but instead send both the projection matrix and the object model transformation matrix to the vertex shader in two separate fields. However, we will stick with doing it this way at least until we cover uniform buffers in an upcoming tutorial. Okay, all that remains to do is actually create a camera instance. Navigate to your application implementation file, and near the top, include the camera header. Then with
First up, CPP. Should include the camera.hppp. After make the cameras in there. Let's
I'll add a
see.
new local variable just underneath the simple render system variable, with type LVE camera called camera and
Movie camera and camera.
get the braces to initialize. Next, I'll set the camera to use an orthographic projection for now, with the arguments -1, 1, -1, 1, and -1, 1. So the orthographic
Let's set the orthographic projection and let's set the -1, comma 1, comma. Set
view
this
volume will be a 1 by 1 by 1 axis aligned cube. Update the render game objects function call to include the camera as the third argument, and then we can build and run the code.
added
And we
this.
get exactly what we had.
Let's hit play. Hopefully everything should work. Yeah, the cube is rotating correctly. Yeah, the window resizing is working as well.
Like to point out is how the cube stretches and squeezes based on the window's dimensions. This is because the viewing volume is a fixed size, so we always map a square viewing volume to the window using the viewport transformation. I first talked about the viewport transformation way back in tutorial 4. As a bit of review, the viewport is a fixed function vertex post-processing transformation. So this transformation is automatically applied following the vertex shader, mapping the canonical view volume to the region of the target frame buffer as specified by the viewport. So unless the window's width and height are equal, so an aspect ratio of 1 to 1, the viewing volume will be stretched to fit. We can counteract this by making the orthographic viewing volume's x and y aspect ratio match the Windows aspect ratio. But to do so, we're going to need the swap chains aspect ratio. In the renderer header file, just under the get swap chain render pass.
The render header file.
I'll add a public function, float get aspect ratio. Mark it const.
What is it? VK render pass get swap chain. Yeah. Okay. Float get aspect ratio. Const done.
And then return LVE swap chain arrow operator extend aspect ratio. Navigate back.
Okay, let's see. Return LV swap chain. Dot extend. Yes. Oh, that's handy. I can just do dot and it will automatically add it. That's nice. Okay, that should be now. I should be now. Client ID. I will just look at what is this client ID then. Guessing it's like some form of linter client ID. C++ linter to its purpose is to provide an extensible framework for diagnosing and fixing typical programming errors. Let me see if I can switch. Say it'll be under tools, I guess. Inspection lens. Left click jumps to highlight, middle click shows intention. Clan tidy. Use clan tidy instead of the built-in one. I use it for C++, general, clan D, built-in inspection. I'll just type inspection. Constraint violations, formatting, incorrect spacing, general, font added, syntax style, CMake, that's general. Oh, you can't see this window. Hmm. Code metrics. Common practices and improvements. Class can unit final. User defined structural show. Intentions. Inspections. C-line formatter. Naming. Syntax style. Braces layout. Linkage. Pivot changes. Tabs indents. Naming. Syntax styles. Braces layout. Anti-brackets. Filling the same line. Different lines. Yeah. Force line breaks. Yeah. Allow comments after. Hmm. Let's apply this. What is this? Client ID function should be marked no discard. Let's see what it shows up. This is good practice. Should be noted that the rules this motion outlines are not the rules the C++ standard committee themselves use for when to apply. Functions like operator new and no discard while functions like optional value are not. The rule stated lag. Do not add for new APIs when not using the return value does not hurt. See, case that is suggested are described in the documentation of the check. Hmm. Moderners use no discord checker as a checker. Added to client ID. I wanted my time to use no discard liberally to catch cases where people were accidentally using a function called empty when they were meant to use clear because developers were coding like list.empty. The presence of no discard or empty forced the catching of some bugs. You can also use, okay, interesting. Let's see any other thing. Yeah, this is official documentation, which return value should not be ignored. Replacement string. Useful when maintaining source code that needs to compile to C++. Okay, let's see. Raw modern is used when function returns marked as a type marked as no discount. Function divide. Okay. I'll add these in at the end of the tutorial once everything is sorted. Because some functions might get deleted here and there. So no point doing it this early. But nice to know at least it has some purpose. Yeah. Yeah. Let's go
to
back.
the application implementation and move the set orthographic projection function call to within the while loop, just under the glfw pull events.
And
This way,
left.
turn LVE swap chain arrow operator
The swap chain. And get extent aspect ratio.
set aspect ratio. Navigate back to the application implementation and move the set orthographic
My leg has gone numb.
projection function call to within.
First tap CPP. Control X. Control V. Okay.
Under the glfw pull events. This way, the orthographic projection matrix will always be kept up to date with the current aspect ratio of the window. Following that, let's declare a new local variable float aspect equal to lve_renderer.get aspect ratio. Then set the left
We can set the aspect ratio for now itself. Float aspect equals LV render dot get aspect ratio. I think I misspelled it there. Shift F6. Yeah. Let me double check the spelling here. Save everywhere, save everywhere.
the negative aspect and positive aspect respectively. Note that these values for the left and right planes only work in this specific case, where bottom equals -1 and top equals 1. The key idea is that the x,
Yeah, we're doing aspect here. Aspect. Save.
viewing volume matches the windows. This means you need to ensure that the right plane minus the left is equal to the aspect times the bottom plane minus the top. If you plug in the values I'm using here, you can see that that is true. And there you go. Now you can see as I resize the cube, it always maintains its dimensions and isn't stretched. Finally,
Okay, let's try this out. Say everything is building. Oh, if you change the frame rate, you change the speed. So this is on my monitor with all my code. This is on the monitor with, what do you call it? With Microsoft Edge running. So this is my laptop screen. This is my external monitor. Interesting. And just increase the speed. That way, I'm guessing it's some frame rate thing. Yeah, I guess the one on my laptop is running on my iGPU, and the one over here is working on my discrete GPU, which is the NVIDIA 2060. And now let's, yeah, it's not stretching weirdly. Okay, let's stop it and minimize this.
let's try out the perspective projection, as this is the type of projection most commonly used in video games. I'll comment out the set orthographic projection function, and just underneath add a call to camera.setPerspectiveProjection.
Okay, let's comment this. Camera.setPerspectiveProjection. What is the FOV one?
The vertical field of view in radians, not degrees. So I will convert 50 degrees to radians using the GLM
Okay, GLM Radians. Can I do dot radians? No. Radian. Radians. 50 dot, dot 0 f.
function. Common values for this typically
Aspect 0.1 10. That to 2.5.
we're looking in the positive z direction. So that means the bigger the z value, the farther away from us it is. And negative z values would correspond to being
Let's run it and check it out. Build fail. Okay, this has to be 10.0. That's such an annoying thing to do each time. But whatever. Let's run it. Okay. Now you can see there's like slightly more perspective. Let me close this and let's try making it like 10 or something. What is FOVF like official? I guess that's 180 or like super high. Okay, this is like way too. Let's do 180. So let's do 80. Let's see how it works. If we bring it out, it speeds up. Interesting. So we're back at 50. Is there a way to like not have to keep typing F? C++ set default number value to float. Std default float. Mm, double A. Mm. Oh, that's weird. It's gonna be close. Let's
behind
continue.
us. At this distance, the cube appears about the same size as with the orthographic projection. And because this projection is also using the aspect ratio, I and will converge at a vanishing point. And that is it for today. We have one more transformation to cover, and that's the camera itself. In the next tutorial, we will extend the camera class to support the viewing transformation. This transformation will make it possible to change the position and direction we're looking at within the scene. So thanks for watching, and keep on coding. Cheers.
Let's go to the next. Let's check the comments first. There's a master of CG tutorials. I just got all of this to work on my own earlier today. It was frustrating to debug. Implementation is clean as always. See, there are no special errors this for this episode. And to use an offline render based on your design for my future video. Is this good? Your solution will avoid ever having parts of the view that we want displayed from being cut off, as mine does when height is less than the width. Let me check this out. LV camera. Yeah. Set perspective projection. Absolute denominator. If aspect less than 1, we flip it. Okay, interesting. But not particularly important, but nice to know. Okay, let's go on to this.
Welcome back to another Vulkan game.
First, let's save everything. There's 13 projection matrices. What are these arrows? Okay. Save everything. Select all of it, commit and push. Let's push it. Can push successful, clear all. Yeah, we'll have to update the title to include motion view and camera projection camera. Let's update. Okay, our title should be updated. Okay, it's updated on Twitch. Let me check YouTube. Okay, nice. Let's check this
The camera
out.
transformation is the final transformation.
Before we continue, let's refresh our mind to something a little different. Let's play a game of chess. Though this was set to random. Yeah. Let's get this. Okay, last time. Let's go here. Attack this. Let's see. Let's oh, we can't move. Hmm. I just attack the queen. To develop our bishop. Let's prevent castling over here. Hmm. If he wants to capture, he can capture. Not. That's not particularly an issue. Hmm. Let's just bring this here. We have better position for it. Let's block this. Anything happening here? Hmm. If I open things up here, there'll just be like 3 pawns. Let's get this here. Hmm. Let's bring this here. Let's attack the rook. With Sir Castle. Let's save it. Hmm. Okay, we can. Hmm. Let's see, anything interesting we can do. Let's take the queen. Push this forward. Let's take this and take this. And just move this forward. Um, let's prevent anything there. Yeah. Hmm. Let's go over here and give it check. Check. Let's see here. And check again. Let's just keep checking. Check again. Oh, triple flop. Let's grab this. What is that? Just like a pawn. Here. Let's check. Hmm. I'll just take that. We have enough pieces. Check. Hmm. I'll just grab it and attack the bishop. Then this. Check. Check. There's probably some faster way to do this. What did I do? Did I just move it back or something? Hmm. Yeah. Mm. I'll just prevent pain. I can still go back. Let's push up. There's definitely a mate somewhere here. I can still go out this way. Oh, I forgot about that. Oh, whatever. I'll just get the queen. That's ladder. Yeah. There were no mess ups in this. I have to see the game do it. Definitely must have been. What, the bot messed up? They definitely made some mistakes. See, sure must. Yeah, like, what happens if. Oh, the thing was still there. Hmm. Okay. What other misses did I make? I wanted me to capture the counter. What other. Okay, those are just like early on. Okay, cool. Let's head back here.
For us to cover in the sequence of steps to get objects from their original coordinates to the pixels of your screen. The camera transformation, also known as the view or eye transformation, allows us to view the world from any viewpoint and orientation. It's as if we could place an imaginary camera within the world and move it around, capturing what it sees and displaying that to the screen. First, let's recap our current process. We start with a 3D model that exists in object space. By object space, I mean the vertex positions are specified relative to the object's local origin. We then use the game object's transform component to create a 4x4 matrix to transform the object's coordinates from object space to a shared world space where it exists along with every other object in our scene. This is commonly known as the model transformation matrix. Following this, we
Let's
currently
speed
apply the
this up.
perspective projection transform, which transforms objects within the viewing frustum into Vulkan's canonical view volume. But don't mix up the perspective projection transformation and then reorienting the view direction to point in the canonical view direction. We end up with frustum will end up getting to the display. is the perspective transformation combined with an orthograph in the camera transformation. The current drawback to our system is that once in world space, only the objects that are within the frustum will end up getting to the display. Essentially, we would like to allow the frustum to be placed at any location and point in whatever direction we wish. Or perhaps a better way to think about it is rather than move the frustum to the objects, we need to move the objects to the frustum. By moving the objects in the world as if we were moving them with some theoretical camera back to the origin and then reorienting the view direction to point in the canonical view direction, we end up with every coordinate relative to the camera's position and orientation. This is known as the objects existing in camera space. So the camera transformation can be constructed with a translation matrix that moves by the negative of the camera's position, since we are moving the camera back to the origin, and then combining that with a rotation matrix that realigns the direction the camera is pointing to the positive z-axis. Translate, then rotate. Let's get to coding. Start.
Oh, interesting. So wherever the camera is, now I'm going to move the objects to that space. To like where it would have been, or like reverse engineering its position.
By opening your camera header file and just underneath
Camera header file.
the member, I will add a new private variable called view matrix. And all
GLM. Let me just restart this so that my autocomplete works correct.
to the identity. This matrix
So is C length and loading? Yeah, it is. Yeah. Start and reassure passive plus engine. Let's all of this get loaded. Why does it keep opening so wide? Non-volt fusions. Switch mode. Read what on target. Yeah, just asking values. Towards memory workflow. Yeah, initial file processing. Yeah, everything should work now. Yeah, GLM mat 4 view matrix.
camera transform. And just like with the projection matrix, let's add a getter function. I'm going to copy the get projection function and paste it below, and rename projection to get view, and return the view matrix instead.
D. Doing a get view. Get view. Return projection matrix. You return view matrix. That's the no
Now, there will be a
discount.
few different ways that are convenient to initialize the view matrix, more than just the three I will show here. So add void set view direction, which will use three parameters. First, a GLM vec3 for the position of the camera. Next, a GLM
Set view direction. Void set view direction. GLM vec3 position direction. Let's
for
hit
the
the
direction the
circle
camera is
off.
pointing. And finally, another GLM vec3 indicating which direction is up. And I'm going to initialize this to a default value pointing in the direction of the negative y-axis. So add equals GLM
Up equals GLM vec3 minus
3, 0, -1, and 0. Next, I'm just going to copy the setViewDirection function and paste it below, and then rename the function to be setViewTarget, as well as change the second parameter
intermediate set view target.
target rather than direction. This method is useful for
Position direction.
camera locked onto a specific point in space. No matter how the camera or the targeted object moves, the object will be held in the center of the view. For the final method, type void setView y, x, z with a GLM vec3 position and a GLM vec3 rotation.
Void set view y, x, z.
Parameters. This last method here will use Euler angles to specify the orientation of the camera. Euler angles are what we used back in tutorial 10 for specifying the orientation of objects using the transform component, and they can be just as useful for orientations I think we previously form component, and they can be just as useful for orienting the camera. We will use the same y, x, z tape Bryan angle ordering that we previously used. Now, the implementation of these three functions I've included in a pastebin link in the description below. It's really just not worth typing these line by line, as it's very easy to make a hard to find typo. So copy all three functions and navigate to your camera implementation.
View matrices based on we're just manually setting these coordinates. XYZ, XYZ 0, 0, set view target minus position. Yeah. Okay.
And paste the function implementations wherever you want, so long as they are within your namespace. So let's quickly go over these. In the set view direction function, these first three lines construct an orthonormal basis. Simply put, an orthonormal basis consists of three vectors.
So here, WUE.
All of them of unit length and orthogonal to each other, so intersecting at right angles. We can use these basis vectors to construct a rotation matrix and combine that with a translation matrix from the camera's position back to the origin to get the final result for the view matrix. Next, we have the set view target method. This one's pretty straightforward. We just use the set view direction method, with the direction being given by the vector from the camera's position to the target object's position. Also, in hindsight, it might have been a good idea to add some assertions checking that the direction provided is non-zero, so you may want to do that yourself. As the third method, we have set view yxz. We start to construct the rotation matrix just as we did back in tutorial 10 for the transform components map4 function. To construct
Any comments about that?
the view matrix, we combine the inverse of the rotation matrix with a translation back to the origin. We use the inverse of the rotation here because
I want to for the uniform buffers.
we want to rotate from the camera's current orientation back to the canonical view direction. This is the opposite of the model transform, where an object starts at the origin in its default orientation, and we rotate it to its world orientation. Alternatively, rather than using the inverse, I could also have just used the negative angle values here instead. Mathematically, it works out all the same. Okay, so rotation matrices have this. It works out all the same.
Move the top view.
And we rotate it to its world orientation. Alternatively, rather than using the inverse, I could also have just used the negative angle values here instead. Mathematically, it works out all the same. Okay, so rotation matrices have the special property that their inverse is simply their transpose, meaning the rows of the matrix become its columns and vice versa. So just as with the set view direction function above, we multiply the transpose of the rotation matrix by the translation back to the origin to get the final view matrix. Okay, now there's not much left to do. First, let's navigate to the simple render system implementation file. And just outside the for loop, I'll declare
Horizons. Let's go here.
variable using auto called projection view. Camera.getProjection multiplied by camera.getView. Every rendered object will use the same
Render with the objects. Okay. That's better.
matrix. So this
Auto projection view equals camera get projection multiplied by get view. Specified.
way we avoid doing the calculation for each iteration of the for loop. Okay, then inside the for loop, replace camera.projection with the projection view local variable. Next, I'll go to my app
And change this projection view.
and let's test out these methods. So underneath where the camera is first declared, I'll add camera.setViewDirection glm vec3 with 0.
And
The camera at
the first action. Last one. Yeah. Camera dot set view direction. GLM vec3
followed by GLM vec3 with arguments 0.5, 0, and 1. So
0.0 of comma 3 0.5 of comma 0.0 f comma 1.0 f.
build and run my code, and now the cube appears on the left hand.
Am I missing something? Set view direction, position direction. Oh yeah, we had already set the value.
I'm going to build and run my code, and now the cube appears on the left-hand side of the window. And this makes sense.
Let's test this out. Okay, it's correctly on the left hand side.
Because if the camera looks
This clipped over there. It's increasing. Okay. And that all worked correctly.
everything within its view should move in the opposite direction, so to the left. Let's try another one. First, I'm going to comment this line out, and underneath add camera.setViewTarget, and I'll move the camera to the position GLM vec3, -1, -2, and 2. It really doesn't matter. I'll then specify the target.
Okay, target is just the like position, and this direction is the rotation.
0, 0, 2.5. If you recall, this corresponds to the center of the cube. So again, build and run, and we see the cube from a different angle, but it stays centered within the window. One more thing. Don't forget about the near.
Okay. So this camera set view target.
One more thing. Don't forget about the near.
-1. -2 and 2. Then says 0 and 2.5.
Our clipping planes.
So
If I move the camera position way back, even though we were still looking directly at the cube, we will no longer be able to see it. I would need to increase the far plane's distance in order for the cube not to be clipped. Okay, we have successfully.
yeah, let's check this out. Okay, we're now at a different angle altogether. Let's try combining these two. Just keep it. Let's see what happens. Okay, let's save.
Transformations. Objects initially exist at the origin in object space. The model matrix created by the game object's transform component will move the object from object space to the shared world space. Every object then has the camera, also known as the view transformation, applied to it. This moves the object from world space to camera space. In camera space, the camera is at the origin, and all object coordinates are relative to its position and direction. I want to re-emphasize that a camera object doesn't actually exist. We just transform the objects from world space as if the camera was there. Finally, we apply the projection matrix. This technical this today. I hope you guys are looking forward to the upcoming change of pace as much as I am. Next video I think will be on game loop timings and keyboard input. So thanks for watching and keep on coding. Cheers.
Okay. Tomorrow's tutorial will be very interesting. Fields with synthesis 20, chrono duration looks different. Okay. So I'll see all of you all tomorrow. Okay, bye.